Hi, this is a lecture on doing stoichiometry with energy. First thing I want to do is show you a video.
First thing we have to do, of course, is to get some hydrogen and oxygen into this bottle, and we're going to fill the bottle with water. It's called collecting the gas by water displacement. We fill it right to the top and invert it into our bucket of water so that there's very little air in there, like that. And Stella, you're going to pick that up for me. And we have two containers of gas, one hydrogen and one oxygen. They are labeled and they're different colors. And because we're going to make water, just a tiny, tiny bit of water out of the gases that we're putting into the bottle, we want twice as much hydrogen, H2O, as we want oxygen. So you have to hold that up. Amanda, you might want to get closer so that you can see it bubble inside. This is where I would say that we would need all of this. Okay. And when it's about 2/3 full, we're going to now put in some oxygen gas. Again, sometimes this is really tight. Okay, that's where I want to go. Once it starts to bubble out, we know it's got enough in it. These two gases are lighter than air, so when I pick it up, we can assume the gases aren't going to fall out right away and hold on to that.
Basically what you gotta do is you gotta light the match. Someone has to hold this, I guess.
Yes.
Light the match, then light the wood splint,
Right.
and then,
Amanda's, you're going to take the cover off.
yeah, not yet. Wait till it's lit, right? Yeah.
And it makes a really loud noise, Amanda.
Yeah, yeah.
So that is the synthesis of water from oxygen and hydrogen, which is obviously very exothermic. So today we're going to talk about doing stoichiometry with energy. So if you remember our mole map, you might want to grab that. We have done everything in here now. With our gas laws, we use 22.4 and 24.5 liters in a mole. Actually, we haven't done this yet, but we're going to do this part of the mole map now, where we can make a mole ratio with the balanced equation and the energy. So let me show you what I mean. So this would be the balanced chemical equation for forming water. And what we can do now is we can interpret the equation like how we know that we can say that there's 2 moles of hydrogen, 1 mole of oxygen, and 2 moles of water when it's balanced. So I can make a ratio between the hydrogen. I could say I have 2 moles of hydrogen for every 572 kilojoules released. So here's our energy in the exothermic. Or I could flip that and put my energy on the top for every 2 moles of hydrogen. I can do that for any substance in this reaction. So I could say, hey, I got 1 mole of oxygen. For every 1 mole, I'm going to get 572 kilojoules. And I can easily flip that over if I want. And then the last ratio is I could write 2 moles of water are going to give me 572 kilojoules, or I can flip that over also. So that's the different part today, that we are going to still use dimensional analysis with stoichiometry, but we can now make a mole ratio between the energy and whichever substance we're involving in the calculation. So you won't have to do all of these. I'm just showing you. So let me show you an example. So here's the question, how many kilojoules of energy are going to be released if you have 25 grams of hydrogen reacting with excess oxygen? So that tells us that the hydrogen is the limiting reactant. So I would want to just always, so I'm really starting here, and I'm going to take my 25 grams of hydrogen, and then I'm going to convert that to moles. So I want to always go to mole. So molar mass of hydrogen. And then you can see my grams cancel. I'm sitting here at moles of hydrogen. And now here's the new part. I'm going to go down and calculate the energy. So I'm going to take my energy, and I'm going to take my moles of hydrogen. So I'm going to put the 2 moles of hydrogen down here. So that cancels with this. And then my energy is 572 kilojoules. This energy is released, so it's implied that it's going to be a negative value. So if you don't put the negative, that's fine, because I already kind of implied it in the question. But if I had just said how many kilojoules of energy are involved in this reaction, then you would for sure want to do the negative value. So when I calculate this, I'm going to get 3,540 kilojoules. So if I have 25 grams of hydrogen, I'm going to get 3,540 kilojoules of energy. So let me just show you a couple more examples and then we'll be done. So the next example is the combustion of octane, which is what we burn in our gasoline cars. So octane is C8H18, and it's a combustion reaction, so it's going to react with oxygen, form water, and carbon dioxide. And I don't believe this one's on your thermodynamic data, so I'm telling you that it's a negative 5,471 kilojoules for every 1 mole of octane that is combusted. So the heat of the reaction is negative 5,471 delta H, and it's also called the delta H of combustion. When it's a specific type of reaction, it doesn't change anything, but that sometimes we call it that. So for this problem, we're going to be starting with energy, which is different than the one we just did. So I'm going to start with that 16,500 kilojoules of energy that's going to be released, and I'm going to make a mole ratio with energy. So I'm going to take my energy, and I'm interested in ultimately the mass of octane up here. So octane is the one I'm going to make the ratio with. So for this one, I would take my energy and I would put my 1 mole of octane, because there's a 1 in front of the balanced chemical equation. So that gets me into moles of octane, and then I want to go to grams, which is just the molar mass. So 114.26 grams of C8H18 for every 1 mole. So then when I calculate this, I will get 345 grams of octane in order to release this amount of energy. Here's one more example. This is methane, which is what I think everyone in EP, this is how we heat our homes. I have a gas stove. Some people do and don't. And then also I have a gas dryer and a gas water heater. So methane, and this is the one we burn at school. So methane is going to undergo combustion. And then they're telling me that 890 kilojoules of energy is going to be released. So exothermic, it's going to go over here. And I would need to always have a balanced chemical equation. So I would need to have 2 waters, and 2 oxygens. So I'd have 4 O's, 4 O's, 4 hydrogens, 1 copper, 1 carbon, 1 carbon. So for this question, they are wanting us to calculate energy, and we're going to start with grams. So we're going to start with 5.8 grams of CH4, go to moles, and then go to energy using that ratio of 1 mole to this much energy. So I would start with 5.8 grams of methane, and then molar mass is 1604. So that gets me from gram to mole, and now I'm going to do that ratio. It's a 1 because there's a 1 here, and that's going to go on the bottom because I want to get rid of my moles and I want to end with energy. So the 890 kilojoules will go on top. And again, released implies it's negative, so you can give a negative or not, I wouldn't care. And when you do that, you get 320, so negative, we're going to release 320 kilojoules of energy.